Hello everyone, this is Praharsh Palanki, and today I'm going to explain you all about Quicksort algorithm, which is a classic recursive divide and conquer strategy. Well, it is one of the fastest sorting techniques available today in the world. Like binary search, this method uses a recursive divide and conquer strategy. The main idea of this algorithm is to separate a list of items into two parts, that is, surrounding a distinguished item called the pivot. At the end of the process, one part will contain items smaller than the pivot and the other part will contain items larger than the pivot, and the pivot element will remain in the middle. The performance of this algorithm depends on how well the pivot is taken. So choosing a pivot element is very crucial in this algorithm. And here I have described it in the tabular format. Numbers less than the pivot is on the left side and numbers greater than or equal to pivot are on the right side, and pivot element is in the middle. And later the steps. You have to initially pick up the pivot element, either random or median, according to the sorted or unsorted array. This algorithm works best mainly in the unsorted array. Okay, the partition elements into two sections. Elements less than the pivot is on the left side and elements greater than the pivot on the right side. So recursively we have to quicksort these two halves down until it is sorted down to one element. So we will get from unsorted list of array we will get the sorted. Later we have an example here. It consists of 8 elements, and initially we have to take a pointer I, and j is here variable and p is a pivot element. I have taken 2152 randomly as a pivot element, and later on here the value of I is incremented because the value of j is less than p. So if the value of j is less than p, we have to increment I and swap I and j. So here I and j is equal, so we cannot swap that. So later in the third step, I have later incremented I because here also 633 is less than 2152. So I have incremented I and swapped it with 2990. Okay. Later on in the fourth step, here j is 4590 and 633 is I. The pivot element is 2152. So as the rule says, if j is less than pivot, then we have to increase the value of I and later on swap I and j. So I have swapped 4590 with 633. So now I pointer points to 633 and j variable points to 4590, and pivot remains a constant, same, 2152. And later on, as if j value is 4590 now in the fourth step, so 4590 is greater than pivot 2152. So now we have to increase the value of j. Now I and j is equal to 633. So later on we have, if j 633 is less than 2152, so I have swapped the value of I and j. The 1248 goes on the right side and 633 comes on the left side. And later the value of j is 1781 and the value of p is 2152. So it is less, so I have incremented the value of I to 1248 and I have swapped it with 1781 to 1248. So later on, proceeding like that, you will finally get an array like this, and here we get the pivot element in the middle 2152 and I is 633 and j is 2152. So the numbers less than the pivot element, here we can see 2152 is in the middle and all the elements on the left half are less than 2152 and all the elements greater than 2152 are on the right side. So later we have to proceed and we have to sort the left array, that is 633, 725, 1781 and 1248 are sorted on the left side to produce 633, 725, and as 1248 is less than 1781, it comes on left side, and the right side part is 2990, 3180 and 4590. That part is again sorted and it's brought down here, and the 2152 part is in the middle, it comes down as it is. So here is a sorted array, that is 633, 725, 1248, 1781, 2152, 2990, 3180 and 4590. So through quicksort algorithm, this is the sorted array we got it for. And later on, here are the properties and stats of this algorithm. The worst case is big O of n square, as if we choose a pivot element, it splits the array as unequally as possible, and instead of n by 2 elements in the smaller half, we get 0, meaning that the pivot element is biggest or smallest element in the array. And in the average case, it is big O of n log n. Suppose we pick the pivot element at random in an array of n keys. Half the time the pivot element will be from the center half of the sorted array. So whenever the pivot element is from positions n by 4 to 3n by 4, the larger remaining subarray contains at most 3n by 4 elements. So the average case is big O of n log n, which is very good. So yeah, no, the quicksort algorithm is not stable because it swaps non-adjacent elements, which in turn messes up the order. So it is not stable. And the extra space is big O of n, which is the worst case for the recursive calls, and this could get on the worst case order n that's going to be for all those recursive calls. And no, it is not adaptive because it uses big O of n log n comparisons even when the input is already sorted, so it is not adaptive. And the key to quicksort's efficiency is properly picking the pivot random or medium, as said earlier. Quicksort works best on unsorted lists of arrays. So here the best case is on the unsorted array, that is picking the pivot element randomly, and the average case is big O of n log n. And the worst case is picking up the pivot element by median, that is on the unsorted or semi-sorted array, that is big O of n square. That is quite rare or avoidable. And later, why is this algorithm the best? Its efficiency on average is big O of n log n, which is a sweet spot. It doesn't require more memory or space in that place. So it's a very good algorithm and efficient.